roughly speaking, right, the omega x, the range space of that right discrete random variable x has a countable or discrete omega x. Now this can happen, let me say it very clearly, right, it can also happen in a continuous for omega, we will see how, right, it is very simple in fact, right, all you have to do is quantize continuous range and you can get a countable, right. What do I mean by quantize? Supposing you have, we will come to this later as I said, but just to make sure that you realize, you get the idea that this is a general concept and can be applied in all experiments whether discrete or not, right. If in a spinning pointer when the output can be any real number between, let us say 0 and 1 normalized, right, you can say if I get if it is between 0 and 0.1 I am going to output 1, if it is between 0.1 and 0.5 I am going to output 2, like that, right, that is a process of quantization. So you can go you can always go from uncountable to countable, but you can't go the other way, right. So that the idea is that, right, when you have a countable range, countable omega x, right, you have a discrete random variable. So the probability that x, the probabilities, the points are only what the points at omega x, other value, right, other points in R on the real line do not have any probability, right, they have probability 0. Okay, so that all the probability lives in this set, this countable set, and that is why you use the term discrete random variable for this. Okay, and the PMF is fully specified by, let me write it out here again, PMF of x by I'll just write it like this. Both of these are countable sets of numbers, right, and so the only requirement is that this has to be 1, that is this. So you can now ask the question, well, why do I need, do we always have to have a more complicated experiment, right, and define a mapping, etc., etc.? Answer is really no, right. You can just say I can define my experiment itself to be just nothing but x, that is also perfectly okay. That means what? My omega itself is just omega x, my omega I is just the xi. So those are what are called directly specified random variables. But the disadvantage is for that experiment you can only define that, I mean you can't define a more meaningful another random variable, that is the only thing. But that is okay, I mean when you want to just specify the when we want to understand the properties of a particular distribution, that is the term we are going to use for this kind of thing, this kind of information. So the probability distribution is how, well let me write it down, right, the term probability distribution, what does it refer to? It refers to is any PMF, right. It is a formal way of referring to any PMF, not just any PMF, it will also refer to the distribution of probability over a continuous interval, that is PDF, that will come later, right. But for now any PMF is basically a probability distribution, right. You think of if you want to say formally, right, you say how is the probability distributed, right. So it refers, so a directly specified random variable is just specified using a probability distribution, right. So to have directly specified random variables, or let me write it like this, we can directly specify a random variable x by setting omega equal to omega x and p of omega I to be, so what do you need to directly specify a random variable x? All you need is a distribution, right? You need the points xi and you need these probabilities. Once you have that, you don't need anything more to specify a random variable, right? So that's what is done in most theoretical, simple problems, right? You don't necessarily have to say, okay, I have this random experiment, I am doing this complicated thing, I am doing this measurement on this point, this is how I am getting x out. All of that is, right, completely circumvented. You just say, let the random variable x be this. That means it is directly specified. So the term directly specified, and directly specify, I forgot the word here, x is said to be directly specified, right? Using this omega x and, or in terms of omega x and the px of xi. That is basically using these two things. So this set of xi is exactly omega x, right? So you are directly specifying, and this is how, right, all the terminologies have come into popular usage, like binomial distribution, Poisson distribution and all that, right, where you are sort of divorcing the random experiment as such, and you are just simply looking at these numbers, right. Okay. Now what else can I do? I can clearly look at events of the form, what kind of events can I look at? I can clearly look at events like x equal to xi, or I can look at x equal to xi or x equal to xj. If xi is not equal to xj, note that x equal to xi is disjoint from x equal to xj. So for any discrete random variable, or any random variable for that matter, right, if xi, right, you have this fundamental disjointness, right, or this mutual exclusivity between x equal to xi and x equal to xj. Are disjoint events. Or mutually exclusive. I think in the beginning I said let's stick to ME, but sometimes we also keep using disjoint, right? It's not I guess it's not a problem. You can switch back and forth. So for xi not equal to xj. So they can never have any intersection. It's just not possible, right? Okay, why do I say this? Because I can now look at, right, I can look at a union event, I can say what is the probability that x takes the value xi or xj, right. So we can ask for, so therefore p x equal to, so I can say x, so this, so e.g. this is a valid event. So this could be some English, right? We're just writing it mathematically in some pseudo mathematics. It's not very rigorous maths in some sense, right? What is the value, what probability that, or what is the probability of the event that x either takes the value xi or it takes the value. Now you can even go a bit beyond this. I can say what is the probability that the random variable x lies between two numbers a and b, right? I can do that also. Even though I am not formally defining the properties of intervals, I can break down that interval into, decompose the interval into the points that lie inside the interval and points that lie outside the interval, right. So extend this to now you have to be very careful when you say between a and b. Do you say open or do you say closed? So you have to be very careful here, because we are talking about discrete variables, and so AB here is an open interval, open at both ends, etc., etc., right. We have seen this kind of thing, right. All of this will become necessary from, right, and So you have to be careful about defining the square bracket for the inclusion and the curly bracket for exclusion. That so you have to say which one you are talking about here, right. So you have 4 possibilities given 2 points A and B. You can either exclude both or include either one, right. So your question could be, what is the probability that it takes values between 1 and 3 but takes value 1 but not the value 3, some things like that, right. So that would be, you including 1 and not including any of those are also possible. So these will be, so these kinds of things, interval probabilities can also be broken down into events like this. So all of these events can be, right, can be expressed how? In terms of x equal to xi. All you have to do is look at all the x equal to xi's that fall in that interval, whether counting both ends or not, as the case may be. So even though we are strictly not, right, we are not including intervals in the list of events right now, because we are saying, well, remember A and B can be totally outside omega x, right, in which case there is no sense in, there will not be any difference whether you include them or not, right. So these interval probabilities will become very basic to study of continuous random variables that some of you have seen, that will come later. But even here, if for discrete random variables also you can talk of intervals, that is all I want to say right now, right. And A and B can be any 2 real numbers, where any 2 real numbers such that, let us say A is less than or equal to B. Of course, does not make sense for it to be equal, because there is no interval if you say, right, A equals B, but I can say, right, between 0.5 and 3.5 or something when x takes integer values, right, and that would be a valid event, because I would interpret it, whether express is the right word or not I do not know, but you can interpret it in terms of events which make sense like this. So whether or not a random variable is discrete, later on we will worry about continuous, you can always talk about intervals, right, without violating the maths, right. Discrete, you are always breaking it, ultimately any of these things you are going to write it down, write it in this form, only because you have only the, what do you have? You only have the p of x equal to xi to work with. So any question regarding probabilities of x, you have to break it down or get it to that form. So you can only have unions of x equal to xi, if you, right, that is what, right, but that does not stop you from asking for the probability of an interval. But when you say interval, you have to be careful, right, because it is discrete, all of these can have different probabilities, because including if A or B lies in x, omega x, including or excluding them will make a difference. Okay, so just be careful when you use intervals, that is all. So we will stop here, right, and pick it up tomorrow. So yesterday we were looking at just basically defining a PMF or specifying a PMF. Important to note that all we require are these 2 countable sets of numbers, right. One is the set of values that the random variable x can take, or any, and need not be just omega x, right. It could have some omega y, or there is no requirement that the label you give that has to be the same, okay, right. You can have multiple random variables with the same specification. That is one very important extension that we will see, right. So we have this bunch of real numbers, right, xi, I have not said that xi is r, but written it out, but it is obvious, right, and then you have the probabilities which satisfy this, right, and once you have this, you are ready to go. You do not have to, you do not require a real life experiment where these numbers actually happen on an experiment and with these probabilities, right. So you are free to look at whatever model you want. Some people just keep inventing models just to suit themselves, right, without any reference to any reality. This is where the subject actually departs from physics or any real experiment, right. You are completely divorced from any physical consideration whatsoever. Anyway, so as I said yesterday, x equal to xi, note, right, these are events, right, and any what else we say yesterday, this a less than equal to x, you may or may not put this you may or may not have the equals whatever, right, depending on this is also events, and these are events which are the union of x equal to xi for whatever appropriate I. Again, I am not being very rigorous about this, but it's we don't need to be very rigorous, right. Just think of this as an event, right, that the random variable x takes values in some interval a b, including or excluding the ends of the interval, right, and write it in this form. So you don't have to create a set at this point, right. It's enough if our sigma field of events includes only x equal to xi. It does not have to you don't have to make a separate exception for saying, oh, intervals are not this. In fact, they are nothing but union of x equal to xi. So just from a mathematical point of view also, there is no issue in treating this as an event, right.